Okay, this is an answer to question B3 on our 2008 final. It's a little bit tougher question, but I hope you kind of enjoyed it. Haha. So here's the kind of payoff table that I gave you in the exam. And basically, there's a series of questions that I asked that about Nash equilibria and driving behavior. The first question, which I'm going to put up here, was use the rows of this figure to explain why the strategy choices in row 1 cannot be a Nash equilibrium. Now, let's have a look at row 1. Okay. If we look at row 1, now, row 1 has everybody driving along route Y. Let's have a little look at the overlay there, what route Y is. That's going from A to Y, then Y to B. So we've got 4 people, 23 minutes each, 4 people, 15 minutes, total of 48 or 38 minutes, just what our payoffs are along here. So basically what we want to do is realize that, I mean, this can't be a Nash equilibrium because any one of the guys, given what the other players are doing, would like to switch to the other route. So for example, let's take the black player here and imagine him switching to route X. Okay, well if he goes from A to X, he's the only guy on that road, so it's 6 minutes. If he goes from X to B, he's the only guy on that road, it's 20 minutes, so that's 26 minutes. Okay, pretty good. And the way to calculate that from this payoff table is to look at the pattern of choices or strategies of the other players. Got them circled here, and here's our black player. So we find in this payoff table another pattern of choices where the other players are doing the same thing, because remember Nash equilibrium is, okay, given what the other guys do, am I making a best response? So while the black player, if you look at his choices, he can go from Y to X, and if he goes from Y to X, his payoffs go from 38 to 26, shorter time. So this can't be a Nash equilibrium because black player isn't playing his best response. And you can do a similar line of reasoning for any one of the other 3 players to show that that row can't be a best response. So let's try question 2. Question 2 tried the same kind of question, row 3. Okay, let's see why row 3 can't be a best response. So what you can think of is we got to row 3 from row 1, where everybody's going on route Y, by the green player switching to route X. And now we're wanting to say, okay, here's one guy using the X route. Let's get back to the overlay over here. So one guy along the X route, 3 guys along the Y route. Does anybody have an incentive to actually deviate? Okay. Well, the way to look at this is to consider one of the players, say, who's got a long travel time, 34 could be red, black, or blue. And what I've done is I focused on the red guy and said, well, given what the other players are doing, Y, X, Y, am I doing the best thing as a red player? So let's find another pattern where there's Y, X, Y down here, Y, X, Y. So that means we're holding the strategies of the other players constant. And he's better to switch to X because his travel time goes from 34 down to 29.9. So the way we show this isn't a Nash equilibrium, is by showing that one of the players, at least one, doesn't play a best response. We don't have to look at the situation from every player's perspective to show it's not a Nash equilibrium. But that is something we have to do for the next question. The next question says, well, what's a Nash equilibrium going to look like? And I'm telling you that it looks like row 6, okay, where 2 guys are going on the Y route, 2 guys are going on the X route. Let's have a look at that. 2 on the Y route, 2 on the X route. So they split their driving. And we want to look at row 6, and we've got to go through and explain that this is a Nash equilibrium. Now here we have to look at it from the perspective of each of the players, red, blue, green, and black. Are they making a best response given what the other players do? Well, let's look at red's situation. Okay, if red changes from Y to X and the other guys stay the same, well, we have to find out where they stay the same. Well, they stay the same down here. Here's a pattern YXX. Then he would be changing his strategy from Y to X. His payoffs would go from 30 to 33.8. So he's actually better staying where he is. What about black? Well, let's look at black. Is he making a best response? Well, given what the other guys do, YYX, and here's the other pattern, YYX. If he changes from X to Y, then his payoffs go from 29.9 to 34. Okay, let's see where we get that 34. Okay, so let's move this down out of the way a little bit. Remember, what's happening is he's switching from X to Y. So he's going along here at X. There's another guy at X. He switches over to Y. So now there are 3 people on Y. Okay, 1, 2, 3. If there are 3 people on Y, 22 minutes here, 12 minutes there, that's 34 minutes. Okay, he's better off staying where he is at 29 minutes, 29.9, just a little under 30. Okay, marching along. What about blue? Well, blue could change his choice from Y to X, but we're trying to examine his change of behavior given that the other guys stay the same. So we're under red Y and X. We find that pattern down here, red Y, X, and X. And we notice when he does change, his payoffs go from 30 to 33.8. Can't be a best response to move to X. So he is making a best response up here. And finally, let's look at it from the green player's perspective. If he chooses to change from X to Y, and the other guys stay the same, so we got YYX, here's a YYX, then he moves up over here, his payoffs go from 29.9 to 34, bad news, so he is making a best response here. And so that's the basic way in which we're able to establish that row 6 is a Nash equilibrium. Okay, now we come to the slightly trickier questions. Let's get rid of this original payoff matrix here. And have a look at question 4, which is, supposing we're in the new game, okay, where there's a new road. And what we want to do is show that the original pattern of driving behavior, where people are splitting 2 Y's, 2 X's, is no longer Nash equilibrium. Well, that makes kind of sense, right? Because there's this new fast freeway in the middle, and somebody's going to be able to benefit by switching, but we'll work it out. And then we also want to show that if everybody has switched over there to this new fast route, that also won't be a Nash equilibrium. So let's march through the reasoning there. We don't use that table, and it'd be too painful to actually construct the whole payoff table, because each player now has 3 possible strategies. So we'd have to have a table of 3 times 3 times 3 times 3, which is like 81 rows, and we don't want to look at that one, okay? But we can just use our intuition here, okay? Let's put up the times and the patterns according to the original split, where red and blue go to the left here along Y, green and black go to the right here along X, and these are their travel times. Now, supposing that one of them switches, let's just look at one. Let's take the red player, okay? So the red player switches from Y to taking the fast route. So he was going along this route from A to B, but now he goes along here to X, okay, and he goes along the new freeway, and he goes along Y. Let's look at his travel times. Well, there are 3 guys now going along X, okay, because remember, we got 2 going along X anyhow, and so travel times for everybody go up to 12. Then our red guy peels off here, and he gets a 7 going along the fast road, and then when he goes along here, there's 2 guys going along there, so travel time is 9, so that's a total of 28. So yes, okay, by switching, his payoffs go from 30 to 28. So this pattern cannot be a Nash equilibrium, because in that Nash equilibrium, the red player can improve his payoffs, assuming the other guys don't make any change. Now, I didn't ask you to do this, but let's have a look at what happens when the red player does switch like this. What happens to other people's travel times? Well, the blue guy goes down from 30 to 29. Why? Because the blue guy is the only guy now looking at this segment here, so he has takes 20 minutes, but then he has to travel with the red guy again on this segment here goes up to 9, so that's 29. What about the green guys? Well, the green guys were sitting here on a nice 29.9, but there was only 2 of them then going along this route. Now there's 3, so the time goes up by 3 minutes to 12. Okay, so now they've got add 3 minutes to their travel times each, so that's 32.9 and 32.9. So you got to be a little careful here, okay? Well, the red guy isn't being careful. He's just taking advantage of the new freeway, reducing his travel time, but he's imposing costs on other people because now he's using this more congested little feeder road here. Now, that's just looking at the question here of whether the original driving pattern could still be a Nash equilibrium, and the answer is no. Let's look at the new driving pattern, where everybody goes on this road, the new route. So everybody's going along here to X, that's 15 minutes each. They go along here 10 minutes each. They go along there 15 minutes each. Ooh, 40 minutes in total for everybody. Okay, so if everybody goes to the new route, then travel times are going way off the map. But is that a Nash equilibrium? Well, no, it can't be, because let's, for example, take the red guy, think about switching away. If he goes back along the Y route, it takes him 20 minutes along this segment here, and then he's got 15 because he's got to travel with everybody else along that route there, so that's a total of 35. So this can't be a Nash equilibrium, because given what the other guys are doing, if this guy makes a change, he's going to be better off. Okay. Let's move to our last question. Now this is a question where we've got to show something is a Nash equilibrium, and that's a little tougher, okay? So we want to show this pattern where 2 people use the fast bit in the middle, and one uses route Y, splits along the outside, one uses route X. We want to show that that's a Nash equilibrium. Well, let's have a look at how we might calculate the payoffs along there. Of see, we've got the red guy going along this route, A. Takes him 20 minutes. He's the only person on that route. But then when he gets to this point Y, he's got 3 other people who he's got to compete with, because remember, these 2 guys here are going from A to X, X to Y, Y to B. So there'll be 12 minutes for him along this route, plus his original 20, so that's 32. What about the black guy? The black guy is splitting over here along the X route. When he goes along this route here, there are 3 X's. Remember, the Y guy, the red guy, is going directly along this route here, so he's not traveling here, but there are 3 X's. 12 minutes now, plus his 20, 32. What about the other 2 guys who are taking the fast route? Well, as they travel from A to X, there's 3 of them along there, so that's 12. Then there's only 2 along here, so that's 8, that makes 20. And the other 3 along here is 12, that's a total of 32. Okay, so total travel times have gone up to 32. Now we want to show that this is a Nash equilibrium, and to do this, we have to go systematically through for each player and show that they're making their best response given what the other players are doing. So let's walk that through. Consider it from the red player standpoint. So we're keeping the blue player strategy the same, the green player strategy the same, the black player strategy the same, and the red player switches from Y to XY. Okay, along here, the red player is thinking, oh, I'm going to try this new short route and see if that's any better. Well, if he does switch, there's going to be 3 of them going along here. Well, actually 4 of them going along here now, so that's 15 minutes, right? Everybody is using the X link in those patterns. Then there'll be 3 along here, so that's 9 minutes, so 15 and 9 is 24. Okay? And then another 12 minutes because there's 3 people each along this link, so that's 12, so a total of 36. So if he switches to XY, from Y to XY, given the other guys are doing the same, then his travel time is going up. Okay, so Y is looking pretty good, but we've got to check out one more option. That is, what happens if the red player goes to X rather than to XY? Okay, remember, there's only 3 possibilities. This is the one we're looking at. He could switch to the XY route, or he can switch to the X route. Well, if he switches to the X route, okay, there's now 4 people going along here. That's 15 minutes. Now 2 people going along here, 20.9 minutes. That's 35.9. Again, his travel time has gone up. So in the original pattern, red is making a best response. Any other choice he has is longer travel lines, given what the other players are doing. Again, I haven't gone and worked out here what the effect of red switching will be on these other guys, because we're not asking that. We're just asking from red player's perspective, if he switches, what are his payoffs? Okay, let's try a switch for the blue player. Blue player switching from XY to X. Okay, so if he switches from XY to X, he was traveling along here, and he switches to X. What's going to happen? Well, he's still got these 3 people. Remember, there's 3, 1, 2, 3 who are traveling along X. That's 12 minutes. If he switches to X, there are now 2 guys on the X route, so that's 20.9 minutes. That's 32.9. 12 plus 20 is 32.9. So his travel time has gone up if he switches to away from the XY to X. What about switching to Y? Well, if he switches to Y, then again there's the second guy. He has the second guy go along in the Y direction. That's 21. He's got 3 people along the Y route. There's 3 guys here. That's 12, so a total of 33. Again, his travel time has gone up. So for the blue player, given the other players are spread out the way they are, their strategies are staying constant, then his best response is the XY route, A, X, Y to B, rather than any one of these other alternative routes. Now you can see by the symmetry, the same analysis will hold if we switch the green guy to a green X or a green Y, because it'll just be the same kind of calculations, given that the blue player and the red player and the black player are staying in their respective positions, or with their respective strategies. Try the black guy. Black guy can switch from X to XY. So his if he switches from route X to going here to route XY, then essentially what's happening is he's still got the 12 minutes going along here. Then he's the third man in the link up here, so that's 9. That's 21, right? And then he's got 2 people on the if the black guy switches to X, he's still got his 12 minutes along here. Oops. Black guy switches to X. Is that X? Or switches to XY. If the black guy switches from X to XY, his travel time is going to go up. Let's see how that occurs. Well, he's still traveling here along X, so he's got his 12 minutes because he's sharing the road with 3 other guys. Then he switches over to the speedy route, which is 9 minutes, so that's 12 and 9 is 21. But then he's got 3 other people on this short route here, so that's 12. So that brings us up to 33. Okay. So if he switches from X to XY, he's worse off in travel time. So X is better than XY. What if he switched to Y? Well, if he switches to Y and comes around this route here, there's one other guy, the red guy in that route. So he's got 21 minutes, and then he's got 15 minutes on this route because everybody's traveling the Y route. Okay, all of these 4 players are ending up using this little segment Y. So that's 15. That's a total of 36. So again, best response is to stay where you are in this set of strategies here, given the other guys are spreading themselves out this way, you're better off at X. So that's how we show that it's a Nash equilibrium. Now, the rest of the question, let's just pull up the old travel times. You can see it was actually better off without that other road. People's travel times are lower before they had this extra freeway than after. And as we've gone through the logic, you can see what's happening is that as people switch to this, away from this pattern to this pattern here, and it looks like it's individually rational for people to switch given what other people do, then they end up imposing costs on other people who are using these short feeder routes that are now more congested. So we do save some travel time on the long segment, but we're increasing travel times on the shorter segments, and the net effect in this example is for travel times for everybody to actually go up. Cheers, John.